Hello everyone, my name is Suhani Nalwar and today I'll be presenting on Generative Adversarial Networks or GANs. These are an exciting area of deep learning where two neural networks compete to improve one another, enabling the creation of highly realistic synthetic data. So let's begin our journey into GANs. GAN architecture. A GAN consists of two main components, the generator and the discriminator. The generator job is to create synthetic data that looks real, and the discriminator's job is to distinguish real data from the fake data generated. This creates an adversarial process where both networks compete, but in doing so, they both improve. Training process. The training of GAN happens in a few key steps listed below. First, the discriminator is trained on the real data and the generator's output to classify correctly. Then, the generator is trained to create data that can fool the discriminator. This leads to iterative improvement where both networks learn from each other in cycles. The generator improves its outputs using backpropagation, gradually becoming better at producing realistic data. Loss functions. The learning process in GANs is guided by loss functions. First, discriminator loss. The discriminator loss measures how well it classifies real versus fake data. Second, generator loss. The generator measures how well it can trick the discriminator. This is structured as a minimax game. The generator tries to minimize its loss while the discriminator tries to maximize its own. These losses are critical in optimizing the parameters of both networks during the training. Applications of GAN. GANs have a wide range of real-world applications. First, image synthesis means creating entirely new realistic images. Second, image editing means changing or enhancing existing images through techniques like style transfer. Third, data augmentation, generating extra training data, especially useful in medical imaging. One notable example in NVIDIA's GAN, which generates stunningly realistic landscapes from simple sketches. The challenges in GAN training. Despite their potential, GANs are very tricky to train. Mode collapse. Here, the generator may produce a narrow range of outputs. Vanishing gradients. If the discriminator becomes too strong, the generator cannot learn properly. Hyperparameter tuning. Getting stable results requires careful adjustment of learning rates and architecture. One solution is DC GAN, which improves stability by using more disciplined network architecture. Recent advances. Several exciting advancements have been made to improve GANs. First, conditional GANs. They allow control over output by providing class labels. Second, style GAN. It's famous for detailed face generation, giving fine control over style and features. Third is stable diffusion, a powerful open source tool making high quality image generation that is widely accessible. Fourth, style GAN 2 builds on the original style GAN, enhancing image quality and making training more stable. Okay, to conclude, GANs are powerful models that can generate highly realistic and complex data. They are widely used across domains from art to medicine and continue to fuel innovations. In future, improving stability and control will make GANs even more versatile and reliable. Thank you. That brings us to the end of our presentation. I appreciate your attention. And now I'd be happy to take any questions from you. Thank you for your attention.